All right, here we go. So related rates are word problems. So people kind of either like love them or hate them. It's like a love-hate relationship with them. I kind of like them because it gives you an actual scenario to wrap your head around. Word problems are just like any other problem. You just have to make sure you put units on everything. So we're going to spend 2 days on this because it just tends to trip people up that there's, a paragraph that they have to read to understand what's going on. So we'll spend 2 days on this. So we'll do a few and then we'll take a break and practice a few more. Just do a bunch of practice. So first you're gonna draw a picture if you need to. Basically you should pretty much always draw a picture. List out what you're given and what you're missing. So I call the missing thing the question mark value. That's like the thing that they're asking for, what we're trying to find. And I usually also try to put a note to myself whether it should come out positive or negative. So you can check and see if your answer makes sense. Like, should it come out positive or negative? Write an equation showing the relationship between the variables. Okay, sometimes that's going to be Pythagorean theorem. If you ever write triangle, oftentimes it turns out that way. Sometimes that's trig if you're dealing with an angle. Sometimes it has to do with a circle. So let me write out some of the common circle formulas. The area of a circle is pi r squared. The circumference is 2 pi r. So that's your area of a circle and your circumference of a circle. Sometimes it will have to do with like the volume of a cone or the volume of a sphere. I would give you those volume equations. They would typically give you those on the AP exam as well. Because I have one on here that has to do with a cone, and I'm going to give you the volume. Well, let me just go ahead and give you the volume equation for a cone right now. Volume for a cone is 1/3 pi r squared h. So that's for a cone. These are for a circle. So you have to come up with some sort of relationship between the variables. And it's going to depend on the situation in the problem. Then you're going to take the derivative. And this is the most important thing that's on here. So I'm going to actually highlight this. Every single variable is with respect to time. So the dy dx stuff that we were just doing, it's like that, except both x and y and z, all the variables are going to be dt. They are all going to be something dt. Every single variable is with respect to time. Right? So that's the major new thing. Okay. And then you plug and chug. You plug in what you're given, solve for what you don't have, and then just make sure you put units in here. All right, so I have a thing that will show us the motion for these problems. So hold on one second. Let me make sure that I have this open correctly here. I think I do. All right, there we go. All right, so let me share my screen and we'll look at the first problem. All right, so this is saying that we have a 6-meter ladder leaning against a wall, and the bottom is being pulled or pushed out, but at the bottom of it is sliding out. So everything is going to be moving here, and I'm going to slide the ladder in a second so you can see it. The question is, how fast is the top of the ladder sliding down when it reaches 5 meters? Now they say also do 3 meters and 1 meter. Don't worry about those. We're just going to solve the problem once. I wish it didn't say that on here, but I can't change it. So we're only going to solve the problem once. So let me slide the ladder and show you what's happening. It is falling. So the x distance, and then it gets back up just like in real life. But the x distance is getting bigger and the y distance is getting smaller. But notice the 6 meters is not changing. The length of the ladder is not going to be any different. It's not an incredible growing ladder. The ladder is 6 meters. Okay. So let me stop sharing. We'll go ahead and write down the information for this problem. So first you want to draw a picture. And in this case, it is a right triangle. And the ladder is 6 meters. And we're calling this distance x and this distance y. So anything in the problem that is constant, like in this case, the ladder, you can go ahead and label with an actual number. But any distance that's changing, you have to label with a variable. So if it's constant, you can put a number. If it's changing, you have to put a variable. Okay. Yes, and just hold on. We're gonna get there. You're on like step 3. I'm still on step 1. Okay. So listing out the given information. So we were told that the bottom of the ladder is moving outwards. This is going this way. at 1/2 meter per second. So our dx dt, again, that's the rate of x with respect to time. Every single variable is going to be dt. That is 1/2 meter per second. And that's positive because this x distance is growing. The bottom of the ladder is moving away from the wall. Now the question mark value, what they asked for is how fast is the top of the ladder sliding down? So this is going this way. So what we're being asked for is the dy dt. That is what we're trying to find, is how fast is the top of the ladder sliding down? And that should be negative because this distance is shrinking. And it's eventually going to get to 0. It'll eventually hit the ground. So I just always write a little note, like, should that be positive or negative? Because then when we get to the end, we can check and see if we got the correct sign. Now here's the thing with these motion problems. Everything's moving. You have to hit pause at a certain moment. So they have to give you a moment to pause at. And they said when the top of the ladder is at 5 meters. So we're going to hit pause when y is at 5 meters. Here's the common mistake. People will put that 5 meters in the triangle. You can't do that. It's not constantly at 5 meters. We're just going to hit pause at that one moment in time. The reason we could put the 6 meters in there is because that's never going to change. The ladder is always 6 meters. All right, so that was step 2. We listed out all the given information. And now we're going to do step 3, which Morgan already wrote in the chat there. This is going to be Pythagorean Theorem. So it's going to be x squared plus y squared equals 6 squared, which would be 36. All right, so now we're on step 4. Take the derivative every single variable with respect to time. So when we do the derivative of x squared, that is 2x dx dt. So every single variable, before it was just y, we would have to chain on a dy dx. Now every single variable is going to be dt. All right, plus derivative of y squared, that's 2y dy dt. And then 36 is a constant, so that rate is 0. What we're saying is the rate of change of the length of the ladder is 0 because the ladder is never changing its length. It is constantly 6 meters. So that rate of change is 0. All right, and then we're going to plug in everything that we've got and solve for what we're missing. So we don't have x listed out here. I'm going to have to come back to that. So we'll hold off on x for a second. Dx dt is 1/2 plus 2 times y is 5. And dy dt is what we are looking for. So I'm going to leave dy dt in there because that's what we're trying to find. Now this happens a lot. You'll be missing something. When that happens, listen carefully. You want to go back to the original relationship and plug in what you've got and solve for what you're missing. So we're going to plug in, what was it? Y was 5. So we're going to plug in 5 for y in the original equation and see what we get for x. So this is just going to be like a side problem here because we're missing something. So we'll have x squared plus 5 squared is 25 equals 36. So x squared would be 11. And so x is square root of 11, whatever that is. And I like the conversation you guys are having in the chat there. Yes, we only do like the math perspective of stuff. We're not taking into account all the physics of it. We're just looking at it from the math perspective. So it's not going to be like quite as intense as it might be in a physics class. All right, and then last step, we're going to solve for dy dt. So I'm going to subtract this over. Actually, the 2 and the 1/2 are going to cancel. So when I subtract that over, it'll just be negative square root of 11. And this would be 10 dy dt. And then I'm going to divide over the 10. So negative square root of 11 over 10. Again, that would be some decimal. Just try not to use your calculator because a lot of times this stuff is not a calculator. Plus, you're better off just leaving it alone. If you type something wrong, it's going to be wrong. And then make sure you put units. Now, this is a rate, so it has to be something per something else. and our units in the problem were meters per second. And we got a negative result like we were expecting, and that's because the top of the ladder is sliding down. All right, let's try another one. So let me share my screen again. All right, so a winch, which is this thing that's pulling in the boat, at an altitude of 20 feet. So it is 20 feet above the water. That 20 feet is constant. It is not an incredible growing dock. Like that is going to stay 20 feet. Is reeling in the rope at 2 feet per second. So this R distance, the rope that's being pulled in at 2 feet per second. How fast is the boat moving when the rope is at 45 feet? Again, they want you to do the problem like 4 times. We're not going to do that. We're just going to do the first one. So let me show you the motion of what's happening. The boat's being pulled in. So since we're being asked, and then it goes right back out, just like in real life, what we're being asked for is how fast the boat is moving. That's the rate of change for X. So hey guys, is our answer going to be positive or negative, do you think? What do you think our answer is going to be, positive or negative? I'm seeing both there. Let me show it again. What is happening to the distance X as the boat gets pulled in? Is it getting bigger or smaller is basically the question that you want to ask yourself. Shrinking. Good. So it is going to be negative. So we should get a negative result for our final answer. All right, so let's draw a picture. The dock is 20 feet high. So this 20 feet is not changing. Again, it's not like an incredible growing dock. So that's going to be 20 feet. And then this is the rope, and then this is the boat in the water. I'm using the variables they used in the problem. You could call them A and B. I mean, you could call them whatever you feel like. I just went with those because that's what it had in the picture. All right, so let's list out what we were given. We were told that the rope is being pulled in at 2 feet per second. So that's our rate for the R variable. So dr dt, and it's being pulled in, so the rope is shortening, getting smaller. So that will be negative 2 feet per second. And then we're being asked how fast is the boat moving. So that's the rate of this x distance. So dx dt is what we are trying to find. And we said that should be negative. And then again, you have to pause at a certain moment. Everything's moving. We can only talk about one moment at a time. So it said when the rope is 45 feet out. So we're going to pause at that particular moment. But again, you can't put 45 in the picture because it's not 45 feet all the time. That's just the moment that we're pausing at. The dock is always 20 feet. It doesn't matter what the time is. It's not going to change. So this again is going to be Pythagorean theorem. It's going to be 20 squared plus x squared equals r squared. So that'll be 400. 20 squared would be 400. And then we're going to do the derivative. So derivative of a constant, that's 0, plus, and then this would be 2x dx dt equals 2r dr dt. Again, every single variable is going to have a dt, all of them. And so I guess you don't really need that 0 in there. And I'm going to go ahead and cancel the 2's. I have a 2 on each side, so I'm going to go ahead and cancel those out just to kind of reduce this. And then we can plug in what we've got. So first thing is x, which I actually don't have. So we're going to have to come back to that. dx dt is what we're looking for. So I'm going to leave that in there. That's our goal. That's what we're trying to find. Equals r is 45. And then dr dt is -2. And so if you are missing something, what you do is go back to the original relationship and plug in what you have and then solve for what you're missing. So we're going to plug in 45 for r right here. I'm just going to do this as a side problem, and we'll solve for x. I'm not really going to have enough room to fit it in over there. Let me just solve this down here. It'll be 400 plus x squared equals 45 squared. I actually don't happen to know that one off the top of my head. So 45 squared is 2025. And then I'm going to subtract over the 400, so that'll be 1625. And then square root, which that's not a perfect square, which actually almost kind of makes me mad because 16 is a perfect square and 25 is a perfect square, but this is not a perfect square. So I'm going to just leave it as that. No, when you type that in, you get 40.31128874. So I'm just going to leave it as the square root. You're better off doing that than trying to put it in the calculator. It's a hands-off approach is always going to be best. And the last step would be to divide that over. So this would be negative 90. You could honestly just leave it as 45 times negative 2 if you wanted. You don't need to rationalize. You can leave the square root in the denominator. That is all fine. You just need to put the units, and this is a rate, and the units are feet per second. And we did get a negative result like we were expecting. So you just always want to check that. Yeah, I'm upset that's not a perfect square too, but it isn't. It just isn't. So. All right, we'll do one more and then we'll take a break. All right, so this is about a cone that is filling up. It is not a magical growing cone. The cone is going to stay the same size. The amount of water in it is changing. And what I want to draw your attention to is, wait, let me wait till it starts over again. Oh, do you see how it fills up really fast at the start, and then the filling up sort of slows down? Why does that happen? Why would it fill up really quickly at first and then the rate would slow down? Why would that happen? Yeah, like you're increasing the amount of water that has to go in. Like the cone just gets larger at the top. So anyway, so it's gonna fill up really quickly at first and then more slowly. All right, so water is flowing into the cone. The height of the cone is 16 centimeters and the radius is 4 centimeters. Again, that's not changing. The cone is going to be the same size. The water in it is what's changing. And the water is going in at 2 cubic centimeters per minute. That cubed is a big clue that that's about volume. Things that are squared are going to be area, and things that are cubed are going to be volume. And so that's the rate at which the volume is filling up. How fast is the water level rising? So they're asking about H. So how fast is H changing when H is 5 centimeters deep? Again, we're only going to do the first one of these. So when it is 5 centimeters. And it's only letting me use that for 20 minutes at a time. So I'm going to have to open it back up again because I don't have the purchase agreement. All right, so we're going to go ahead and draw a picture for this. Here's the cone. And they told us that the height of the cone is 16 centimeters and the radius of the cone is 4 centimeters. And again, that's not changing. It is not an incredible growing cone. The height's gonna be 16 centimeters and the radius is gonna be 4 centimeters. Now the water in it is what's changing. I'm gonna draw some green water here. So this is what's changing, and so we have to label that with a variable. So they called the height H and the radius R. All right, so then let's list out some of the other stuff they gave us. They told us that the volume was filling up at 2 cubic centimeters per minute. So that is the rate of change for the volume. So I'm going to call that dV dt. And then what they asked us for is how quickly is the depth of the water changing. Now I know they called it depth, but what they're talking about is the height. So dH dt is what we are trying to find. And guys, should our answer be positive or negative? If the cone is filling up, what's happening to the height? And good, it should be positive. Awesome. That should be positive. And then again, you have to pause at a certain moment. This water is changing, so we have to decide what moment we're talking about. And they said when the height is 5 centimeters. Now, your relationship between the variables is going to be the volume of the water. So you need the volume of a cone. And I would give this to you. That is your volume formula for the cone. Now, here is the issue with this. We have a little bit of algebra to do, so you can't be scared of the algebra here. There's going to be like 3 or 4 steps of algebra before we can do a derivative. Here's what the problem is. We have a radius and we have a height, and we do not have any information about the radius. So I have to substitute the radius out of there. I cannot do this problem with the r value in there because I have no information about r. So I'm going to have to get rid of that. So here's what we're going to do. Look at this picture. And this is going to be, you're going to have to remember back to geometry class, which I know was like many years ago for you guys. Do you see how there is a big triangle and a small triangle inside? I always, when I taught geometry, I called them the mommy triangle and the baby triangle. But do you guys remember similar triangles, like the triangle that's inside of the other one? This is like ringing any bells here? Because we're going to set up a ratio between these. Oh, that. Okay, good. I'll take oh, that. All right, so for the mommy triangle, the big one, 16 matches up with h. We're going to have 16 over h equals, and then 4 matches up with r. So equals 4 over r. So that is our ratio that we're going to set up, and we're going to cross multiply. So that will give us 4h equals 16r. And I want to get r by itself. I have to substitute out r. I have no information about r, so I have to get rid of that. So I'm going to divide the 16 to the other side. 4/16, good, would be h over 4. I'm going to write it as 1/4 h. That means the same thing as h over 4. I just like having a coefficient. All right, but here we go. This is going to get substituted in for r, and you cannot be scared of the algebra. We're going to have to get through it. It's like 3 or 4 steps. You're all going to be okay. That's my pep talk. You're going to be fine. We'll get through it together, right? So we're going to substitute 1/4 h in for r, and then kind of simplify this down. So the first thing that's going to happen is we have to square what's in the parentheses. It's like order of operations here. So the exponent comes first. So if you square a 4th, you're going to get a 16th. And if you square h, you're going to get h squared. So I just squared what was in here. And then I'm going to multiply all this together. So a 1/3 times a 16th would be 1/48 pi. And then I have an h squared times another h. So that would be h cubed. All right, so that was like 3 steps there that we had to get through the algebra. But hey, look what we have. We have something that is very simplified and only has h in it. So the rest of this is going to be not too bad. You cannot be scared of the algebra and the simplifying to get through that, because it's necessary in some of the problems. All right, so now we're going to do the derivative with respect to time. So derivative of v is dv dt. And then here we're going to bring the 3 down. So that would be 3/48. You can write 3/48 if you want, but that would be 1/16 pi h squared. Again, power rule, you're going to drop a degree. So I brought the 3 down. That was 3/48, which is 1/16 pi. Drop a degree, and then dh dt. And then we're going to plug in what we've got and solve for what we're missing. So dv dt is 2. And h is, where is it, 5. Now you can get as fancy as you like with this, but here's my suggestion to you. Again, hands-off approach is always going to be the best. If you want dh dt by itself, all you want to do is divide all of this to the other side. You just want to divide all of that over. And so I would just write it as 2 over all of that mess. On the AP exam, it's the grader's problem at that point. That's their problem to have to look through that and make sure that it's right. I would just do almost nothing, because if you make a mistake, it's not going to be right. So just divide all that over. And then the last thing I need are units. Now this is a little tricky. We were given centimeters cubed per minute. That was the rate of change for the volume. We just found a rate of change of the height. So it's just this distance. So that's not going to be cubed like the volume was. So it will just be centimeters per minute, because it is not a rate for a volume. It's just a rate for a height.